Okay, so we are now going to move on to section 2.2, which is limits involving infinity. So this is on page 12 in your notes. You're going to want to have a graphing calculator handy for this. So we've talked about this before, especially end behavior. So when we say, the limit of f as x approaches infinity, what we mean, what happens to the y values as x gets bigger and bigger. So what happens to the y values as x gets bigger? So that's the limit as x approaches infinity. Okay, so when we talk about the limit as x approaches negative infinity, we mean, again, what happens to the y values as x gets smaller. Okay, and we can figure this out from just knowing the general, shape of a graph from parent functions, or we can look at the graph. So when we look at this function here, f of x equals 1 over x, so we know that's our parent function, it's a parabola. As x approaches infinity, 1 over x, so the y values are getting closer and closer to 0. And so we write the limit of f of x as x approaches infinity equals 0. Okay, so as my x's get bigger, what's happening to my y values? They're getting smaller, 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 getting closer to 0. Okay, so then as x approaches negative infinity, as x gets smaller and smaller, what happens to the y values of 1 over x? They are getting bigger, but they're leveling off at 0. So the limit of f of x as x approaches negative infinity is also 0. Okay, when your limit is a number, how that's going to show up in your graph is as a horizontal asymptote. And that horizontal asymptote is going to correspond to the values of your limit. So our horizontal asymptote is going to be at y equals 0. That was something that we saw again back in chapter 3. Okay, so then our definition for a horizontal asymptote is that the limit as you approach, if the limit as you approach infinity is some value b, and the limit as you approach negative infinity is some value b, then that line, y equals b, is your horizontal asymptote. And if just one of them, it doesn't actually have to be both of them, if just one of them approaches a number, that is going to be a horizontal asymptote. So example 1 is asking you to use graphs and tables to find the limit of these functions, and now all of these functions are going to be ones that you feel like, oh, I've seen that before, I know what the parent function is. So that's where you're going to want to maybe use the graph or the table. Okay, so I already have this graphed. Let's see, not too bad of a glare. Okay, so I already have this graphed. And I want to think about, okay, well, what's the limit as x gets bigger and bigger? So I'm doing two things. Again, when I'm talking about end behavior, or as the limit approaches infinity or negative infinity, I'm thinking about what happens to the y values as x approaches infinity and negative infinity. Okay, so here's my graph. It looks like it's leveling off here at 1. If you couldn't tell that, there are a couple of things you could do. So one is you could hit Control T and look at the table, and you could just start scrolling and seeing, okay, it seems like it's getting closer to 1, and then you could go backwards also. Another option you have is if you go to Menu, and then 5 for Trace, and 1 for Graph Trace. You see, you get the little cursor there, and it gives you the value, and you can just type in any x value you want. So I'm just going to type in the number 10, and you can see it just shows up right there, and hit enter, and it will show me where it falls on the graph, 10, and it's telling me the y value. And I can type in any number I want, so I could type in 100. So I just started hitting the number 100, that pops up, I hit enter, and then it's so close to 1 that it's saying the value is actually 1. So as I put in bigger and bigger values of x in that graph trace option, the y values are getting closer to 1. And I could see what happens as x gets smaller and smaller. So let's say I put in negative 10 and hit enter. Okay, I can see it's negative 0.999. Okay, because this doesn't look like it's leveling off at 1. Let's see where this is leveling off at. Kind of looks like maybe negative 1. Again, I could plug in maybe negative 100, and I can see up there it is, negative 1. So this has two horizontal asymptotes. Okay, so this has, here are my limits, and it has horizontal asymptotes at y equals 1 and y equals negative 1. Okay, make sure you're writing those as equations, not just saying 1 and negative 1. Okay, those are equations for lines. Okay, so now let's move on and look at our graph for part B here. So here it is. It's a hyperbola, really, that basically ended up getting shifted. And so it's looking like it's leveling off at 1. So as x's get bigger, my y's look like they're getting closer to 1. As the x's get smaller, it's looking like my y's get closer to 1. And again, I could confirm that by tracing my graph. So if I went to, again, menu, and then 5 for trace, and then 1 for graph trace. And right now, it's starting at 0 and saying that's undefined, which we know because 0, it would be 0 in the denominator if we plug 0 in. But if I plugged in, let's say 10, it's 1.1. If I plugged in 100, it's 1.01. If I plugged in 1,000, so I'm plugging in bigger numbers to see what happens to my y values. Okay, so the limit of f of x as x approaches infinity, and in this case, negative infinity. So if I wanted to be fancy, I could write plus or minus right there. I'm just going to write them separately because I didn't really leave myself enough room. In both cases is 1. So in this case, my horizontal asymptote is at just y equals 1. So in this case, I only have 1. Okay, so let's see this next example. So this next example is talking about the sandwich theorem, which we did not talk about in the first section. So we're not going to really worry about, I feel like I didn't graph this one. So we're not really going to worry about the sandwich theorem part of it. We're just going to look at the graph for this one. Okay, and I noticed that actually I have the wrong graph here. So I'm going to insert a graph, and let's put this in here. Thought I had them all loaded in. Apparently not. Okay. So here's my graph. Or maybe we remember that from the other day when we had it in our notes. Okay, so the red one here is what we're looking at. So you can see it's kind of wavy, but the values are getting smaller. So it seems like, and this is just asking for the limit as x approaches infinity, that seems like it's getting closer to 0. Again, we could confirm that with the graph trace. So if you want to do that, you could confirm that with the graph trace. Okay, I'm going to actually get rid of this one. Okay, so let's move on to the next page. What do we have here? All right, so properties of limits as x approaches positive and negative infinity. So last time we talked about as we approach a number, all those different properties, same properties hold if it's approaching positive or negative infinity. Now the thing though with these properties is you have to be a little bit careful because sometimes if you use the properties, you're going to get one answer, but if you looked at the whole thing, you would not be able to get an answer at all. So we kind of have to be careful with how we're using these properties. Okay, so for this, if I were to split this up using my property, so if I were to look at this, let's say, as the limit as x approaches infinity, I'm going to split this into, I'm going to rewrite this as 5 over x plus sine of x over x. So I'm just kind of breaking this apart. And then I'm going to split it into the limit of both of those expressions. Okay, and we did a little bit of this in section 2.1. Okay, so then this becomes the limit as x approaches infinity. This would simplify to just 5. And the limit of a constant is just a constant, plus the limit, oops, I need this, as x approaches infinity of the sine of x over x. We just talked about that one and said that that was 0. And so we get the limit as 5. So using the properties, we get the limit of 5. Now the thing is, if we were not to have split it apart like that, and let's say we had looked at it in two different pieces. So let's say I looked at it as f of x is this and g of x is this. And it's asking, do the limits as x approaches infinity of f and g exist? Okay, so if I were to graph these separately, okay, so you might want to, if you're doing this at home, pause the video and do it separately. Like, go ahead and graph that and see what it looks like and find the limit as x approaches infinity. So if you want to pause, go ahead and pause. Okay, I've already graphed that, so here's my graph for 5x plus the sine of x right here as x approaches infinity. For this right here, I'm getting a limit of, I would say, infinity. As x gets bigger, it goes up forever. All right, let's look at the next one here. Okay, and then here's this guy here. The limit of this is infinity. And so if you were trying to figure out of it overall, you know, the limit of this overall, you might think something like, well, maybe the limit is infinity, you know, divided by infinity. Is that my limit? And then say 1. I don't know. Can you even divide infinity by infinity? Okay, but that's not what we got. So it says, can we apply the quotient rule to f of x over g of x, right? So no, that doesn't make sense. But does the limit of the quotient exist? Yeah, we got an answer right here. All right, so the idea is that we just kind of have to be careful about how we're using those properties. And it's going to be the same idea with this second one. Again, it's asking if we let this be f of x and this be g of x to find the behavior of each of those. Okay, so here is, and again, you might want to pause it and look at the graph it yourself and think about it yourself first before you watch this. Okay, so here's my sine squared of x, and what is my limit as x approaches infinity? And in this case, we don't have a limit, right? So limit means as x gets bigger, your y values are getting closer to a particular value, and these just keep going up, down, up, down, up, down. So this we would say the limit does not exist. Okay, and if I were to graph, here's my cosine squared of x, and if I look at that one, it's kind of the same idea. We would say the limit of that does not exist. But what if we had written this as the limit of that sum? Okay, now take it back to chapter 7. Well, that was one of our identities that we used all the time. You might remember the limit of the sine squared of x plus cosine squared of x, that value, rather, just equals 1. And the limit of 1 is 1. So when we look at things individually, like using that property, we would get that the limit doesn't exist. But if we use properties that we know, like special properties of functions, then that limit actually does exist. Okay, so the whole point of this is to really be careful about how we're using those properties, because some functions have special properties that allow us to do things. So here in part 3, if you graph each of these individually and think about the limit. So if we look at it, here's our graph for the natural log of 2x. And if you're thinking, okay, what happens as x gets bigger, what's happening to the y's? It might seem like that levels off, but it's logarithmic. It grows just really slowly. So in this case, the limit of f of x as x approaches infinity is infinity. And if we were to look at the next one, the g of x, as x approaches infinity, it's another logarithmic graph. And again, it's increasing but really slowly. So we would say that's also infinity. But then if we tried to use the difference rule on this, remember we just did all this stuff with logs, and logs have special properties. So this we could actually rewrite as the limit as x approaches infinity of the natural log of 2x over x plus 1. And if we look at the graph of that, here it is. Now this one's a little bit different. It's not infinity. So if we look at that graph, it does look like it's leveling off. It looks like we have a horizontal asymptote. Now I can't really tell what it is, so I'm going to do menu, and then 5 for trace, and 1 for graph trace, and I'm just going to put in bigger numbers. So when I put in 10, I get 0.598. If I put in 100, 0.683, 1,000, 0.692, 10,000, 0.693. So it seems like that's leveling off at about 0.7. So the limit of the difference did exist. And so the big idea here is just be careful, because sometimes functions have special properties, like trig functions, right? All the different log rules that we've talked about. And sometimes that's going to affect things. Okay, I'm going to pause there, and then we'll pick up again in a minute.